All right, welcome to our first physics video this week. There'll be 3 of them, and we are starting in our last unit. I combine unit 4 and 5 together because unit 4 is the wave nature of light, and unit 5 is modern physics. And to be honest, I don't like the way the textbook orders it. So they're so close together, and one really leads into the other. So we just follow my handouts, follow the videos, and we are going to be starting with special relativity. And we have talked about relativity before in class. We've gone over many times relative velocities, relative motion, frames of reference, inertial frames of reference, non-inertial frames of reference. So just a quick example. Let's say we had a car moving this way at 100 kilometers per hour and a car moving this way at 100 kilometers per hour. Now, if you're standing over here on the road, you see, well, this car moving to the left at 100 kilometers per hour and this car moving to the right at 100 kilometers per hour. However, if you're in this car, from your point of view, how fast are you moving? 0, right? You're not moving at all from your point of view. And from your point of view, how fast is the other car moving when it passes you? 200 kilometers per hour, right? Right? Okay, well, in that case, it kind of makes sense, doesn't it? Well, let me change the question then. And this is where the problem comes in. Let's say I'm in my car and I've got a very fast car. I'm moving at 3/4 the speed of light. Yes, I have a fast car. And I drive by this other car. It was also moving at 3/4 the speed of light. I don't know where he got that car. This is the unique car. It's the only one around. All right, so if I'm standing over here at the side and I see this car, I'll see it moving at 3/4 the speed of light. And I see this car, I see it moving at 3/4 the speed of light. But let's say I was on this car. How fast would I see that car moving? Think about it. If you followed the same logic as you did with the previous question, you would simply add the velocities, right? Or, well, subtract the velocities if you're paying attention to the direction, but you would add their magnitudes. And you would get 1.5 times the speed of light. That breaks a very important law of physics. Nothing can go faster than the speed of light. Certainly, nothing with mass can go faster than the speed of light. And if you don't have mass, well, then you're already traveling the speed of light. So basically, if you're not already traveling the speed of light, you never will. So what's happening here? Why can I not say that I see that other person traveling at 1.5 times the speed of light? Why not? Obviously I can't. We have a problem here. So I'm going to move ahead in the PowerPoint here. So Maxwell discovered that light is an electromagnetic wave with Maxwell's 4 equations. We went over that in the last unit in electromagnetism. He also discovered that the speed of light, this is very important, the speed of light is always the speed of light. What do I mean by that? Well, okay, let's look at another example. Let's say we have a photon of light moving in this direction. Well, what's it moving at? It's moving at speed of light, c. Let's say I'm standing here. How fast do I see that photon move by me? I see it move by me at the speed of light, c. Okay, great. Now I'm going to get in my car again. I'm going to go this way at 3/4 the speed of light. How fast do I see that light travel? At 1/4 the speed of light? Does that make sense? It doesn't. And Maxwell showed that the speed of light is always 3.00 times 10 to the 8 meters per second, regardless of your frame of reference. So if I'm moving this way at 3/4 the speed of light, I will see that photon pass me at the speed of light. This is a little weird, Well, what if my friend is over here? He sees the same photon pass him at the speed of light, but he's not moving. Well, relative to me is moving, but relative to him, I'm moving at 3/4 the speed of light, and the light's moving at the speed of light. Relative to me, the light's also moving at the same light is moving at the speed of light. What's going on here? And it is quite confusing. And we're going to go over a little experiment on the board here. And then I'm going to put a couple other videos, some really good videos that talk about light in a different sense and go over some other visual experiments so that hopefully you can get the idea of what special relativity really is. But I'm going to move forward with this experiment. So we're going to take this experiment. We're not going to use cars anymore. We're going to go right into space. Okay. Now let's say we're on a spaceship. Now on this spaceship, we have two mirrors, right? And let's say I do an experiment. So I'm on the spaceship. I do an experiment where the light goes up. And then it can reflect and come back down. It's going to go up at the speed of light. And if I know the distance there, I can calculate the time, right? Or I could use a stopwatch if my reactions are really fast. But either way, let's say I figure out the time it takes for the light to go up. I don't know, maybe 3 seconds. Yes, this is a big spaceship. All right. Well, let's look at this from another point of view. Let's take my spaceship and let's have my spaceship move very fast at some velocity v. I don't know what it is. Maybe 3/4 the speed of light, half the speed of light. Some velocity v which is less than the speed of light. Well, how is this going to look from somebody floating around in space? Okay, well, at some time, let's call this t0, the light beam is here. It's just about to leave. But then when it reaches up here, the spaceship has already moved. So now the spaceship has moved from here to here by the time it reaches here. So it's actually, from my point of view, the light beam looks like it's doing this. But from the point of view of the person on the spaceship, it looks like the light beam is doing this. Okay? So it's almost like the light is traveling a different distance in the same time. Let's analyze this a little bit further. All right, so let's look at the distances then. Now this distance, if I wanted to calculate this distance, well, distance is just velocity times time. And the velocity is the speed of light. So the speed of light times the time. I'm going to write delta t naught, meaning the time measured in the rest frame of this experiment. So this experiment is being done on the spaceship. So measuring the experiment, measuring the time on the spaceship is going to be our rest frame, and that is going to be delta t naught. All right. This is what the person sees floating outside the spaceship. No, how fast is the light traveling? We have to follow Maxwell's rule, because he proved light always travels at the speed c in all frames of reference. So the question is, what time is he going to measure? Will it be the same as t naught? If we were to write down t naught, that would be a huge assumption. And it's an assumption many physicists made for many, many years. We're not going to make that assumption. So let's just write delta t for the time. We're not going to put a naught. All right, well, let's finish this triangle here. We also have the spaceship moving. So in the time it took the light to go from here to here, the spaceship has moved some distance. How far? Well, the spaceship's moving at some velocity v. And since this is being measured by the same frame of reference as the person floating outside the spaceship, I'm going to write the same time delta t as that one. And this makes a nice little right angle triangle. Now I love this derivation because we can simply use Pythagorean theorem to figure this out. So a squared plus b squared, a squared plus b squared equals c squared. So let me write this. v delta t squared plus c delta t naught squared equals c delta t squared. Okay, let me make this bigger now. I should have done this earlier, sorry. There we go. All right, so here's our Pythagorean theorem. All right, let's just put those squares in there. So we got v squared delta t squared plus c squared delta t naught squared equals c squared delta t squared. All right, now the next step I'm going to do is I'm going to bring all of our delta t's to one side and our delta t naughts to the other side. So I'm going to move this over there. So over here I'm left with c squared delta t naught squared, and on the other side we have c squared delta t squared minus v squared delta t squared. Okay, so now let's make it a little simpler. I'm going to just erase this and divide every term by c squared. Right, so we get delta t naught squared equals, well, c squared divided by c squared is the same here. They just cancel. Delta t squared minus v squared over c squared times delta t squared. All right, let's factor out a delta t. Okay, now I'm going to divide both sides by this and take the square root. So we're going to have our time, which the person measures from the frame of reference outside of the spaceship, is equal to the time that the person measures inside of the spaceship, divided by the square root of 1 minus v squared over c squared. Now this 1 over 1 minus v squared over c squared appears everywhere. So we actually gave it a term. We gave it the term gamma, which is actually called the Lorentz factor, because 10 years before Einstein came out with his theory of special relativity, Lorentz did the mathematics, but Lorentz didn't actually understand the mathematics. He just thought, here's some math that makes everything work. Where Einstein came and said something else. He said, well, look at this gamma factor. Now, in everyday circumstances, you're in your car that's not traveling 3/4 the speed of light, maybe 100 kilometers per hour. Okay, change 100 kilometers per hour to meters per second. It's like 30 something. So take 30 squared and divide it by 3 times 10 to the 8 all squared. That's a very small number divided by an enormous number. Almost zero. Not quite, but almost zero. It's like 0.0000000, and then eventually there'll be a number. And 1 minus that is pretty much just 1, so you get 1 over 1. Okay, great. That whole term is just 1, so you get delta t equals delta t naught. Makes sense. Both observers observed the same time for the same experiment. But what if that spaceship is going very, very fast? Right? What if it's going 3/4 the speed of light? Well, then the Lorentz factor suddenly becomes something else. You get 1 minus 3/4 c squared over c squared. The c squared is canceled. You get 3/4 squared. That is not 0. Okay? If you want to test it on your calculator, let's do this now. 1 divided by the square root of 1 minus 3/4 squared is 1.5. Well, 1.51185 and so on. That is nowhere near 1. Well, okay, it's close to 1, but still, you can't approximate it to be 1 because you have huge errors now. And if we write that into this equation, well, time that the person standing or floating, not standing, floating around outside the spaceship measures is 1.5 times the amount of time that the person on the spaceship measures. So what's happening here? What's happening here is, well, if this person measures a time of 2 seconds, this person measures a time of 3 seconds. Now that's crazy. You can expand that if you want to. If this person measures a time of 2 weeks, 3 weeks, 2 years, 3 years. So for the same event to occur, this person aged 2 years and this person aged 3 years. And this is what Einstein says. He said, going back to our earlier problem, where you have two different people in two different frame of references seeing light travel at the same speed of light, how is that possible? It's possible because time is moving differently for each of those observers. Okay, so take a minute, let that sink in. Okay, I know we've talked a bit about time dilation with the general relativity, and yes, gravity does slow down time, but also moving fast does the same thing. Okay, so let me go back into small mode here. Why does this keep open? Okay, now this leads to a lot of things, like the simultaneity postulate, which says just because two things happen at the same time for one observer doesn't mean those events occur at the same time for another observer. Okay. This we all went through. The Lorentz factor. Now note that gamma must always be greater than or equal to 1. Right? We've kind of shown that. There's no possible way that it would equal something less than 1. If you're going faster than the speed of light, well, then you're going to get the square root of a negative number, and that's like, no, you can't do that. Well, you could use complex numbers, but there's no real solution here, right? And that comes from part of the reason we can't do that. We can't even reach C. V can never be C. V must always be less than C. And because V must always be less than C, gamma must always be greater than or equal to 1. So there's a time dilation. You could rewrite this equation as delta T equals gamma delta T naught. But that's not the only thing that happens. We have a couple other things that happen. We have length contraction, right? Which means if you have an object moving in this direction at faster than the speed of light, an observer will see or measure that object's length to be less, right? So if you were to travel the speed of light, well, look what happens in those equations. If you were to travel the speed of light, time would not pass, and your length would fall to 0. That's weird, right? So I don't even think you'd want to travel the speed of light if you could. But something else happens. Your momentum changes. Okay, we've looked at this equation, P equals mv. But let's say you're trying to add energy to an object. And you're doing work on this object, and therefore adding kinetic energy. Well, remember, we can't go faster than the speed of light, so we can only add so much kinetic energy. But we can still do work on the object. It's just now that kinetic energy, or sorry, that work, reaches a limit to it being able to transfer to the object's kinetic energy. At some point, it's going to start transferring to the object's mass as well. Now, when I say that, I don't mean it gets massively bigger. Remember, length contracts, right? But its effective inertia increases. And so it's harder to actually change its momentum, because its inertia has increased. In a sense, its mass term has increases. Okay, so let's look at the back. Now there's a question. There's 2 questions. Question number 1. Well, actually, there's a little statement here. I'm going to put a video from Minute Physics that's going to go over that. But then there's an example. Okay. Now there's also another question which goes over. Oh, sorry, that's tomorrow's lesson. I'm getting ahead of myself. We just have one example, but I am going to post other YouTube videos. So in this example, we have a pi meson. No, sorry, a k meson. Okay, it's a subatomic particle. You haven't learned it yet. That's okay. Just we have a subatomic particle. We'll learn about all the different particles towards the end of this unit when we do a couple lessons on particle physics. But we have a subatomic particle, and it's not very stable. In fact, its lifetime is only 1 × 10⁻⁸ seconds, and then it's gone. All right, and that's its rest lifetime. That means if you were looking at it in its rest frame, that's how long it would live. But it's not in its rest frame. In fact, it travels through your laboratory at 2.6 × 10⁸ meters per second. Okay, well, since it's traveling, think about it this way. If you're in the laboratory and you're watching it move, is it going to live longer from your point of view or shorter? This is the hardest part about this equation. The equation is easy to substitute values into, but the hard part that students find is, what am I solving for? Delta t or delta t naught? So in this question, the rest lifetime is 1 × 10⁻⁸ seconds. What is that? Delta t or delta t naught? Okay, and I gave you a hint when I sort of introduced this equation. Delta t naught, right, is the time measured in the rest frame. And so this question is giving you the value for delta t naught and the value for v. So we're not even going to need to rearrange that. We're just going to plug in our values and we'll get an answer right there. All right. So I don't think I need to put in my solution. My solution is right there in the PowerPoint. You can pause the video and look at that. So I won't post that, but I am going to post this video along with a couple other videos to help explain special relativity. Okay? Until next time.